Nice to see everyone here. Thanks for having me. I'm just gonna kind of go over a few data sets that are out there that are at least in my sphere of knowledge. Um, and specifically, I'm going to be looking at things that are coming from constellations. But I thought, maybe before I move on to the next slide, I could give kind of a preface to this in terms of thermospheric densities or data um, relating to the thermosphere. Um, this I think measurement of the thermosphere really started in earnest in kind of the late 50s and 60s as people began tracking satellites with ground-based radar systems, and that technology lives on today through the DoD's program to track a handful of objects, about 90 or 100 objects, that they then feed into the HASDA model, which is the high accuracy satellite drag model. That's kind of the operational thermospheric model for the DoD. This is a kind of a protected model, so not a lot of, for instance, commercial constellation owners can use it. Um, that's anyway, that the tracking is one data set that's been out there. In the 60s and 70s, they started developing accelerometers and mass spectrometers that they could send up and get things like a total mass density for the accelerometers, or a chemical composition, temperature, and even sometimes winds from mass spectrometers. The heyday for those was really in the 70s and 80s. And in the last 40 years, we have not flown, to my knowledge, a single successful mass spectrometer in the thermosphere here at Earth, but the state of the art has lived on in missions like MAVEN at Mars and other planetary missions like that. Um, um, in the kind of the modern era of the accelerometers, started in the early 2000s with the CHAMP satellite and the GRACE satellite, and Goche, and to some extent Swarm, and what's flying right now is Grace Follow On. So these are Earth science geodesy missions that the thermosphere community has been able to leverage. But this is kind of the landscape of thermospheric measurements, and so um, we've tried to find what we kind of refer to as signals of opportunity or data sets of opportunity, where um, you have a lot of tracking data from for instance, a satellite constellation of thousands and thousands of satellites, and I'll get to that in a minute, um, or just other things that are out there that we can make use of. So that's kind of the preface to this. And of course, we talked about in earlier talks today, we've heard about the space traffic management concerns in LEO, so I won't go into that too much, but I will say there's quickly becoming a sustainability issue in LEO, where we're launching a lot of things, and if we're not careful about where we put them, for one, and how we keep them from colliding, for two, then we're going to have pretty big issues in the coming years. And so this is a nice graphic from ESA, showing that it's okay to launch a lot of things if you do it low enough in the atmosphere, because if you have any kind of collision or catastrophe, things will fall out of the atmosphere in a reasonable amount of time. And as you travel up into the atmosphere and you're launching things higher and higher, um, you're very quickly creating a debris field that is never going to come down, at least in our lifetimes and our grandchildren's lifetimes. So the issue there is, so you want to launch your satellite constellations in low Earth orbit, very low in orbit. But on the other hand, you have to deal with this quite variable environment of the thermosphere that's moving your satellites around and making it hard to track them with any accuracy, making it hard for you to figure out what's going to collide with what. So there's a sweet spot somewhere there. And I think in the space weather community, one of our jobs, one of our tasks, is to grow that sweet spot, make sure that we can predict the variability of the thermosphere, so that you can launch much lower. So that's the idea here. So one of the first things I'll talk about is working with the Starlink constellation, which is you know, as you can see from some of the information here that I've pulled from Wikipedia, they're a constellation that began in about 2019. They've got several thousands of satellites here. I haven't updated this number since the last talk I gave, but it's grown several hundred since then. So and so what we're doing is we're working with SpaceX, which is the owner operator here, and we're using their position and velocity measurements, their tracking measurements, to estimate what the thermospheric density is around a given satellite. And for this case study, we're working with about a year's worth of data. And during this time, from April 2022 through the following April, there were about 4,000 satellites in orbit then. And we're working with about the first 1,500 of those, and I'll show some results of those. And so basically how this works, I won't go into this in any real detail here, but you have GPS measurements of some kind giving you pretty continuous tracking. You apply an orbit determination filter, and that helps you to separate the gravitational from the non-gravitational accelerations. You continue with your modeling, and you figure out what proportion of that non-gravitational acceleration is due to radiation pressure. And you keep going and keep separating out forces. You get down to what you consider to be the atmospheric drag acceleration of that satellite. And at that point, you can apply a force model, which is basically what, kind of similar to what you would have seen in Physics 101, a coefficient of drag times a reference area times a density of the atmosphere and a velocity squared kind of term. So, and what we can get out of this is after you've seen how the satellite moves over one complete orbit, you can assign an effective density over that orbit. Or what's really done is you can take a density model that is uncalibrated, and you can provide some scaling to correct that density model. And see, and so we're doing that. Here's an example of one satellite over that year-long period. And we're comparing that with the HASDM model, this routinely calibrated model here in blue, and one single Starlink satellite, one of the earlier ones that they launched over that year. And we see pretty good agreement. Our biases, there's a little bit of a bias, 5, 6, 7% bias there. But our standard deviation is pretty good when we compare those two things. Now, if I were to take all of the 1,500 satellites that I'm working with for this study, process these in the same way, and then calculate sort of an annual mean ratio, I would get this plot. So here I'm looking at that ratio, that data to model ratio over an entire year for about 1,500 satellites. And this is the satellite ID number here on the x-axis. And so we get, again, pretty coherent performance out of all of these different satellites that are in different orbital planes and behaving differently. About 4 or 5% offset between the DoD model and our data set, and about 10% standard deviation. And I showed some outliers there, but if we look at some of the housekeeping from the satellite operators, we can really get, we can kind of reject some of the satellites that are not behaving and improve the performance there. And here's just another way to look at this. And so, kind of as a heat map of the number of data points in these bins, when I compare HASDM to the Starlink densities, the yellow bins, you're seeing hundreds of thousands of data points. So that's certainly a good thing to have when you're thinking about assimilating data is tons of observations to work with. And so this is a more recent time period. This is February of this year. We had about 1 month of data during this time period. And now I'm organizing it into a certain Constellation shell, and then it's sweeping through each plane. So each plane in kind of longitude or local time, however you want to think about it. And what I'm showing here is the time series of the densities. The gray is the density from, say, 20 to 30 satellites per plane. And the black is just a mean of those. And then I've done the same thing to run all of those orbits through the Hasdam model. And so you see something similar here. And here we have the ratio data to model over that same time period. And I've taken a kind of a two sigma standard deviation envelope here in the greenish curve here. And basically anything that peeks out from behind that, any of the gray points that peek out behind that, you can probably safely reject and use these for data assimilation. So that's sort of in some ways that's a low fidelity data source, but it's a high quantity data source. We get kind of the tracking data from Starlink, and we don't really have a lot of we can't put our hands on the raw GPS data, so it's kind of a product that's been massaged in a certain way for their intents, and we try to make it useful for us. But we can also provide a little bit of a higher fidelity method to work with satellites that have more pristine tracking data. So in this case, we've worked with Grace Follow-On for one that has a nice science grade GPS sensor, and also the ICESat-2 satellite. Of course, the quantity isn't there, but the quality is very high. And so we're refining these kind of techniques, just looking forward to the future. So that's this is I think a 6-month example of what that looks like for the ICESat-2 satellite, and this is work that's being done also at Space Weather TREC by Zach Waldron. So just a quick summary here of these kind of object tracking data sets. They can have excellent horizontal coverage. Certainly the Starlink constellation has tons of satellites, and we can use many of those to get out densities. The commercial tracking data sets are going to scale with the crowdedness of the LEO environment, so that's a good thing. And the noise, of course, can be offset by just the sheer large quantities of volume that we have. The kind of the downsides here, though, are they're sometimes limited in altitudinal coverage. So we have these shells of satellites. Starlink is kind of centered around 550 kilometer altitude. So there's not a whole lot of knowledge of what's going on in the vertical domain. The spatiotemporal resolution is not great because you're averaging along an entire orbit. So there's that, and there's some other issues and assumptions that we have to make. So these are all kind of the limitations of this. The last thing I'll say in this, and Fabrizio brought this up, but so the Geospace Dynamics Constellation is an up and coming mission that we're hoping will get through Congress and the president's budget and launch in a few years. And this will be the first time that we've had a mass spectrometer and various other sensors all together on a satellite in the thermosphere, in the Earth's thermosphere, in 40 years. So there's a lot of information we cannot get from these orbit averaged mass density measurements, and GDC is going to really fill in that information and help us improve models. Basically, GDC is slated to help us understand how energy gets into the system and how it moves around in the system to produce the space weather variability that show up in our Starlink data sets, but we're not always able to interpret them from that, or even have our DA systems interpret them in a meaningful way. So this is a really important mission, I think, for our community. And one of the interesting aspects there is that they will have a space weather data relay built into this in each of the 6 satellites, a real-time data source that will be beaming down in situ data to whatever space weather operators want to receive it. So I think this is important. It's one of these developments where NASA is kind of providing something that would be very, very useful to NOAA and other operational partners. So with that, yeah, we've processed, in terms of the Starlink data, we've processed about a year's worth of data, a little bit more than that since I made this slide, but we've also processed several high fidelity POD density data sets, and we're developing techniques that improve the process over what we're doing with Starlink. In the future, we are going to be demonstrating data assimilation with these data sets. There's a couple of methods that are out there that are kind of tailored to this kind of data. So we're going to be using those as part of the Sword Center. We'll be working with JEDI. That's our intent and our goal, to get some of these DA methods into JEDI. So and then I'll leave you with the GDC icon here to to think about. So
thanks, Eric. John, what do you want to do? We can have a couple questions maybe for the data itself, and then we can bring up our slides.
I have a question. Okay, so that was a great presentation. I had a question for you. Related to the Starlink data, I think this is really fascinating. This is actually a really new constellation, a new way of looking at very novel observation operators, and I think it challenges the old business model that data assimilation used to work. So basically, in traditional sense, we had a new satellites, we would have somebody become an expert on it and hand tune everything, and when you have 6,000 new satellites, you can't do that anymore. So that actually has a lot of new interesting challenges. I had 2 small questions about it. One is, do you have any intuition in terms of the correlations of errors within the constellation? Can you treat them completely independently, or do you have to look into sources of combined errors? And the other thing is about data access. How much can we actually get the data, and with what kind of latency?
Yeah, I think thank you for the questions. Great questions. So yes, it is very organizationally, it's very difficult to work with that many satellites and that many data points. But in terms of the error correlation, that's sort of what I was trying to get at with the kind of the animation plot there of looking at February. You can see a lot of the at least the model to data, if that's what we're talking about, is kind of our error or difference in those 2 things. They're very well correlated with each other when you organize things within an orbital plane. So that was really promising to see that. And then it's sort of a quality control issue from there. Things that don't correlate well, or spikes that you see, you're not always sure what's happening. So it's just better to throw it out. And you're not throwing out, you're not throwing out 50% of the data if you do that, but you're throwing out 10 or 15% maybe. And so that's sort of what I've done so far is just trying to get the quality control down. But yeah, the correlation between different satellites, I think that is, I'm seeing that now.
Can I make another component of that? So Tom, you made the statement, and you're right, that this is sort of a new mode, 6,000 satellites. And what Eric is producing is really a very derived data product. And normally in the neutral atmosphere data assimilation system, a data assimilation person will say, I want the raw data. I want radiances if they're doing microwave data or infrared data or something. And assimilating the equivalent of radiances would be carrier phase measurements or pseudo range measurements and that is just like so far. I think that's not a reasonable thing. I could be wrong, but that is, you have to, I think this community has to think about assimilating derived products a lot better. I just think.
Yeah, I'll follow on to that. So a lot of data sets, you have a longitude and latitude ascribed to a specific data set, and some you don't. Like TEC, you have to sample the model along a ray path to and kind of add up the densities along that to get the TEC value that the model would give you. And this is the same thing. You really have to sample the model along an entire orbit and then do that same processing that's coming up with your effective value. Yeah, and then your second question was on availability of data. Currently, there isn't any. We're working with SpaceX through a data agreement that we have, and SUE through SWPC also has their data agreement, I believe, as well, or an NDA. But we're hoping in the future we'll be able to come to an agreement with them as to what we can release and what they're comfortable with, and hopefully, and it may even be something like a reanalysis type data set.
Thank you. Really interesting talk. And I agree with a lot of the points. Yeah, like POD is not a model we want to, but you mentioned you're working on the force. So when that's kind of the final, when you're getting that to your density, right?
Right.
So that's one with perturbations on that, I think probably would be appropriate.
Yeah, Nick.
Yeah, I have a question. Yeah, it's kind of for Eric, but it's also a more general question. You mentioned a lot in the same orbital plane are sort of correlated. So I would wonder, how much additional information are you getting? And that kind of leads into the question of, do you need 6,000 or is 100 enough to do data assimilation? And, do we really have an understanding on that or not?
Yeah, in fact, that's one of the important questions that we're looking into is how many of the satellites do we need? So if you have one plane worth of satellites, there could be anywhere from like 20 to 60 satellites in that plane. What processing all of those together gives you is an idea of the statistics, and that's really, really handy. And it also gives you, once you know the statistics, you can look to see where the outliers are, and of course reject the data. But one thing we're looking at now is, if we take individual planes and request all of the data for those planes, build up the statistics, that's great. But then maybe we don't request every single, sometimes some of the shells have like 72 different planes in them. Maybe we need 6, so we're looking at that. But yeah, thank you.
Other data set? Other talks? And we'll move into the discussion. Thanks, Eric.
Okay. So now we go into the discussion about observation.